is minus yz dm, x squared plus y squared dm, z squared dm, minus xy dm, minus xz dm, minus yz. Okay, good. So dm, of course, is, well, dependent on the mass distribution. It's differential amount of mass. But that's not what's important, because this is constant for the object. Only depends on the object's orientation with respect to these axes. Well, I mean, these axes are defined by the object, so, doesn't change. Okay, so the only independent variable is this unit vector, the axis that we choose. So I'm going to use spherical coordinates because it's easier to express magnitudes that way. And remember, this is a unit vector. So this unit vector is going to be, don't remember the conversion coordinates. Let me check my notes. Cosine theta sine phi, sine theta sine phi. And of course, you'll notice that the magnitude of this is 1. So multiplying everything by rho, the radius, which happens to be 1 here, will just give you rho. Okay, so this is our unit vector. Now, let's unleash carnage. So this all is what? Well, we abbreviate everything as IXX, IYX, IZX, IXY, but that's the same as YX, IYY, this is IZY, this is IXZ, which is the same as ZX, this is IYZ, which is the same as ZY, this is IZZ. Okay, so here's the thing about being rotationally symmetric with respect to the z-axis. That means that with this definition of the z-axis, IXX is going to be equal to IYY. This is not going to be differentiable in any way from that, right? What's the difference between these two? So, erase that. And furthermore, it makes all of the off-diagonal products of inertia 0. Okay, so everything's gone, except these guys. So now, let's get down to the multiplication work. So we know this is equal to this this. So we have cosine theta sine phi, sine theta sine phi, cosine phi, multiplied by, this should be horizontal, but I don't care, IXX, IZZ. Once again, cosine theta sine phi, sine theta sine phi, cosine phi. Okay, so what's this equal to, this product? Well, this times this is just IXX cosine theta sine phi. I'll write it vertically. Then you have IXX again, sine theta sine phi. This multiplied by this column. Then this multiplied by this column is just IZZ cosine phi, which when dotted to this gives what? Well, you have to realize that this is kind of just multiplying the vector by itself, sort of. So you have IXX cosine squared theta sine squared phi, IXX sine squared theta, oh crap, It's not a vector. What am I talking about? This is all Ixx cosine squared theta sine squared phi plus Ixx sine squared theta sine squared phi plus Izz cosine squared phi. Of course, cosine squared plus sine squared is 1, so that gives Ixx sine squared phi plus Izz cosine squared phi. Now, you look at where the maxima for this is located. So to do that, you take the derivative, which gives you by the chain rule, should be 2 sine theta or sine phi cosine phi multiplied by Ixx plus, well, what's this going to be? Izz cosine squared phi. The derivative of that is going to be 2 cosine phi sine phi. Negative sign. Is equal to 0. So either sine phi cosine phi is equal to 0, or Ixx is equal to Izz. Oops, wrote them in the wrong order. Now, of course, this is only true for a spherical object. So in general, we're just looking at this case, which happens when either phi is 0, sine of 0 is 0, or phi is pi over 2, which makes cosine phi 0. Now recall that phi in spherical coordinates is defined, if this is x and this is z, it's defined as this angle right here, which means that at 0, it's somewhere on the z-axis, and at pi over 2, it's somewhere on the xy plane, which means that this implies either a maxima or a minima of the moment of inertia on the z-axis, which makes this a principal axis, and further implies this, phi equals pi over 2 is where the other principal axes lie. Even though this is not very specific, we can go on to show, using very similar methods, that these two in specific happen to be the other two principal axes, which give the maxima or minima, depending on Ixx and Izz, of the moment of inertia. So that means that x, y, and z are the principal axes of this object if it's rotationally symmetric around z. That's it. Thank you, everybody, for watching.